Alright, so last time we looked at the optimization in several variables, two variables in particular, and we looked at when we were optimizing a function for all x and y, and we started the second derivative test, right? We found the critical points, and we used the second derivative test to find the minimum or maximum. However, it's a lot of times what happens is that you don't necessarily want to optimize for all x and y. X and y are within some region where things make sense, right? If I have, I'm trying to find the maximum temperature in a room, well, it should be in the room. It shouldn't be outside the room, right? So I'm probably going to have my my variables are going to be constrained to some region. So let's talk about the kinds of region that we want. We really want set S of the Euclidean space, so maybe of the plane. Let's just do it in two variables. So set S of the plane is bounded if it's within a certain fixed distance of the origin. If it is a fixed distance of the origin. That means it does not go to infinity. So, for example, if I have if S is defined by, let's say, x between -1 and 1, and y between 0 and 3, then this is bounded. It's bounded. Why? Well, if we draw the x, this is y. If we draw actually I have these squares when I use the fact that this is a square paper. Okay, so maybe I can make better drawing. Suppose this is y, this is x, and we have, so x is between -1 and 1, and y is between 0 and 3. So 0 and 3 are here. So this is the region S. Right? Now that's bounded because, well, it's all within a certain fixed distance. For example, I could you can see that these points are the ones that are furthest away from the origin, and the distance over here is well, it's square root of 1 squared plus 3 squared, so square root of 10, right? So that's everything is within square root of 10 of the origin. Similarly, if S is, let's say, x is positive and x squared plus y squared is less than 3, then this is again bounded because, well, if we look at what this region is, this gives all the points that are within square root of 3. So here, So this would be approximately the circle of square root of 3, but also x is, I guess I drew it a little bit, maybe 1 is somewhere over here, not exactly on the on those lines, but we have, so this would be the circle of radius square root of 3, and x bigger than or equal to 0, so we have to be within square root of 3, and we have to be, x has to be bigger than 0. So this is my s, right? So here this is definitely a bounded region, because, well, we have that the distance from the origin is at most square root of 3, right? So almost by definition of the region. So that's what a bounded region means. Now we also want S is closed, and I'll be a little bit vague about this, but essentially it means if S includes its boundary. So what does that mean? That means that let's look at some examples. So, for example, x strictly between 0 and 1, and y strictly between 0 and 1 is not, if S is given by these inequalities is not closed. Why? Well, it's if I look at I suppose this is where 1 is. Is this region, but it does not include these lines, right? Because it does not include the points where, let's say, x is 0, so it does not include these points, or the points where x is 1. It does not include these points, and same for this and this, right? You really have to make all of these less than or equal to make it a closed region. Similarly, if I have S is all points such that x and y are not the origin, well, then it's maybe a little bit hard to draw. It's everything except this point, and that's not a closed region. Not closed. So this is also not closed. By the way, the regions that we defined before, the two bounded examples, these were both closed. They included the boundary over here, and it's included the boundary over here. Right. Now, here we actually have an example of an unbounded region. This is S is not just not closed; it's also not bounded, because it's all the points except for the origin. So there's points arbitrarily far away from the origin. There is a theorem that says that if f is a continuous function on a closed and bounded region, then f attains a minimum and maximum on the region. And the minimum or the maximum, it could be inside, it could be in the interior of the region, not on the boundary of the region, or it could be on the boundary. So it could be anywhere, but it has to be a closed and bounded region. So let's maybe first get some non-examples out of the way. So for example, 1 over x squared plus y squared does not attain either a min nor a max on its domain. If I take all the points x and y where this is defined, which means all the points outside of the origin, all the points where x and y is not 0, 0, then we saw that that's neither a closed nor a bounded region, and this is a function that does not attain either a minimum or a maximum. It does not attain a minimum because, well, if x and y can go to infinity, then this is the square of the distance from the origin, and this is 1 over the square of the distance from the origin. So if I go very far away from the origin, then 1 over that is going to be arbitrarily small, but it's never going to be 0, right? So it's almost as if the minimum would be 0, but that's not attained anywhere. There's no one point where this is 0. 1 over something can never be 0. Now, similarly, it cannot get any maximum. I mean, there is no maximum at all. This can be arbitrarily large, as if 1 over something very small, right? If the distance from the origin is very small, then I have 1 over something very small, and that's arbitrarily large. So it cannot. There's no upper bound on this function either, right? So there's two things. One, it's not bounded. I can go very far out, and that's why it doesn't. In this particular case, it doesn't attain a minimum, and it's also not closed because it does not include the origin, which would be a boundary of this region, and so it does not include that, and that's the reason why it doesn't include, why it doesn't attain a maximum. All right, so maybe if we have this example that sort of shows both of the ways that this can go wrong. Let's see where this can go right. Let's look at a function. Let's let f(x,y) be x squared plus y squared on. Let's do where x and y are between 0 and 1. So this is when we are on a, let's suppose this is where, so this is the origin, where 1 is, x, y, so it's this region over here, right? And we're looking at x squared plus y squared over here, and let's see if it what it attains. Let's look at a graph. So here is the graph. So we have I plotted it from where x is between 0 and 1 and y is between 0 and 1, and you notice that the function has a minimum at the origin and maximum at when both x and y are 1. But notice that the minimum, that is where actually the derivatives did vanish, but it's also on the boundary of this region. It's where is at one of the corners of this square, and the maximum is also on the boundary, but actually the derivative did not vanish over here. And that's, I mean, in general, that's going to be actually true. That if we have if the minimum or the maximum happens on the boundary of the region, then it's not going to be a critical point of the function as if it would be on the interior. So you have to be a little bit careful about that. Basically, you have to figure out what the minimum and maximum is by looking at the boundary, by looking at the function on the boundary. We'll see a more complicated example in a moment. Over here, you can easily figure it out. It's the since it's the square of the distance from the origin, it's clearly is the far corner of this square. That's where the maximum is, and it's the corner at the origin, which is the minimum. Okay, so let's do an example, slightly more complicated. So find min and max of f of x, y, which is going to be x times y minus x squared. All right, and let's do it on where x runs between minus 1 and 1 and y runs between minus 1 and 1. Now that is a region that's both closed and bounded. Looks sort of like this: x, y, and you're running from minus 1 to 1 and from minus 1 to 1 in both the x and the y directions, right? Now, if we want to do this, then the process of figuring out what's the maximum and the minimum of this is a sort of two-step or actually multi-step process. So first, you have to figure out could the minimum or the maximum be inside, somewhere inside here. And for that, we need to figure out the critical points. So I take the derivatives. So f sub x is y minus 2x, and f sub y is x, right? So critical point if x is 0 and y minus 2x is 0, right? And the only way that we're going to get both of these to be 0, well, x has to be 0, right? And if x is 0, then y is 0, right? Because then this just says y is 0. So the 0, 0 is the only critical point on the interior. Okay? So let's figure out, is it a saddle, is it a maximum, is it a minimum? So we can try the second derivative test. So for that we need to find the second derivatives. So if I take second derivative over here in terms of x, I get minus 2. Fxy, if I take the y derivative, I get 1. So that's the mixed derivative, and if I do fyy, that's just going to be 0, right? So if I write down the discriminant, then this is f sub xx times f sub yy minus f sub xy squared. In this case, it's just a constant. It's minus 2 yy times 0 minus 1 squared, right? So now from this, if we look at this is minus 1, so it's less than 0, so that means that 0, 0 is a saddle. Alright? So this is not going to be either a minimum or a maximum, right? So let's figure out, if anything, on the boundary. So how do we figure out the boundary over here? Well, we basically have to parameterize these lines that form the boundary of our set, right? So maybe let's start with this line. This is where y equals -1, right? That's this line, right? And we're gonna do it from x is -1 to x is 1. All right. So what we look at is the function. Well, we said y is -1 and x is between -1 and 1, and so I'm looking at f of x minus 1, right, which I just plug in and I get so x times -1, so I have minus x squared. All right, so that's my function out here, right, on this line, and I just need to figure out where is it, what's the minima and maxima on this interval. And this is basically calculus 1, right? So we sort of repeat the same procedure, again and again. Well, first we figure out at the endpoints. Now the boundary is just these 2 points, right? So it's easy. We can just evaluate the function over there. So we'll get f at -1, and so that's going to be, well, if I plug in -1 over here, right, I'll get just +1 and minus -1 squared, right? So let me write this, and you can see that writing the parentheses is important here, right? So it's if we have minus, this is 1, right, and this is -1. This is 0. Okay, so the function is 0 over here, right? And this is where f is 0 out here, right? Now, at the other endpoint, f at 1, -1, well, this is very similar, except I plug in 1. And you can see it now, it's -1, so this is -2. Over here, I have f is -2 at this endpoint. All right, so now I just need to figure out, well, so I have somewhere where the function is 0, somewhere where the function is -2. What about in between? Can it take something that's bigger than -2 and bigger than 0 and less than -2? So, well, let's look at that. So we have let me just rewrite what we have so that we don't forget. This was xy minus x squared, and we are looking at the function x minus 1, right, which is minus x squared at between -1 and 1. All right. Now, if in calculus 1, how you would do this? Well, you would again find the critical points. So you look at the derivative of this guy. Well, the derivative of this guy with respect to x, right? This is just a function of x. That's the same thing as plugging y equals -1 into the x derivative, by the way. So this is f sub x minus 1, and so that's I just differentiate with respect to x, right? So -1 minus 2x. All right. Now, where is this 0, right? So I'm looking for the critical point. So -1 minus 2x equals 0. So that's minus 2x equals 1, or x equals -1/2. All right. So that's a critical point. So now, if I could use the second derivative test from calculus 2, but I actually know I have on a bounded interval. I've checked the endpoints. I know that f at when x was -1, it was what was it? This was when f this -1 was 0, and f at 1 -1, this was -2, right? So I just need to figure out what happens here, and just basically I want to figure out the maxima and the minima. I just need to figure out the maximum and the minimum of those three numbers, right? So well, let's just plug in. So I have f of -1/2 -1, and so that's minus -1/2 minus -1/2 squared, right? So this is 1/2 minus, well, this is like 1/2 squared, so it's -1/4, right? So this is 1/4. All right. So I have these guys. One quarter. Okay, so this is not going to be this guy is not going to be a minimum, but that's going to be, at least on the boundary, on that piece is the boundary. It is a maximum, right? And the -2 is the minimum, and 0, well, it's neither a minimum nor a maximum. So and I guess the graph just on that boundary would look like this, right? Where it would be 0 over here, it would be -2 over here, and it would be a quarter over here. So, well, this is it would be something. This would be the axis, right? So, all right. Well, let's continue, right? I could do the same exact thing now for y equals 1, right? So when y equals 1, f of x1, right? I'm plugging y equals 1, is going to be x minus x squared, right? So now the derivative of, well, let's maybe check it first at the endpoints, since I guess we did that last time first. So -1, 1. So this is -1 minus -1 squared. So it's -1 minus 1 minus 2. F of 1, 1 is, well, I have 1 minus 1 squared, 0. So it looks very similar to what it was before. Now let's look at the critical points inside. So, well, inside this little piece of the boundary. So it's f sub x 1, and that's just the x derivative of this. So it's 1 minus 2x. So that's 0 at the whatever the critical point is, and that's at x is 1/2, right? So I just need to figure out at 1/2 what do I get? 1/2, and y is still 1, right? So I get 1/2 minus 1/2 squared, again a quarter, right? So again, I'm getting a quarter as the maximum on this little piece of the boundary, right? So far, I've done this piece of the boundary and this piece of the boundary, right? And I got, what did we get? We got 0 over here. Somewhere over here we got a quarter, and here we got a -2. And here we got -2. Then somewhere over here we got a quarter, and somewhere well, at this corner we get a 0. Okay, so now, well, let's look at the vertical sides, right? So on the vertical sides, these guys, right, on that picture, this is where x is -1. This is where x is 1, right? Let me copy it here just so that we have it written down, is still xy minus x squared. So let's look at f of well, let's look at this side first. So this is x is -1. Y, well, y is whatever y is, right? So if I plug in -1, I get minus y minus -1 squared, so this is -1. Okay. Now over here, this is just you know, a linear function. In particular, if I take the derivative over here, which is just the y derivative of f, well, it's just -1. It's never 0, right? So I'm really just looking at the endpoints, right? Meaning I look at f with -1, -1, right? And we actually did that already, right? This was the thing was 0 over here, right? And over here it was -2, right? When x was -1 and y is 1, right? So this is if you plug it into here, you see that that's -2, right? Now, okay, so that's this little piece of the boundary. Well, let's look at this little piece of the boundary, right? That would be, so this was when x is -1. Here, when x is 1, it's almost the same, except now we have y -1, and so again, the y, you know, if I differentiate this thing with respect to y, it's just 1. I get 1, right? It's never 0, and I just look at the endpoints, and so 1 -1. So it's this is when we're right over here, and this is where we got -2. Right? We already did these. We already looked at them when we were looking at the top and bottom bit, right? And over here at 1, 1, we got 0. Okay, so that means that overall, fxy is xy minus x squared. Actually, it's minimum on when x is between -1 and 1, and y is between -1 and 1. At well, where did we achieve it? At -1, 1 and 1 -1, and the minimum is -2, and f achieves a maximum of 1/4 on the same set at well, this was when we were over here and over here, right? When x was either minus 1/2 and y was minus 1, and over here it was when x was 1/2 and y was 1. All right. Well, let's look at the graph and see if this really works. Okay, so here is the graph of x times y minus x squared. You can see over here, you can see the saddle that we found at the origin, right? This is where the origin is, right? So above the origin, there is a saddle, and you can see where we found the you know, what the function was on the different sides, right? So when y was -1, then we had this curve that went up from 0 to 1/4, and it went down to -2, right? And similarly, when y was 1, it started at -2, went up to 1/4, and went down to 0. And so that's when we had that one critical point on those sides at x equals 1/2 and x equals -1/2. And then on the remaining sides, on x equals 1 and x equals -1, we just had a linear function, right? We just had there were no critical points, right? It was basically, it just had that y minus 1 and minus y minus 1. So it's so we didn't get any new candidates over here, right? And so you can see that the minima of -2 were achieved at 1 minus 1 and minus 1 1, and then the maxima were achieved at these 2 points over here, where x was -1/2 and y was -1, or when x was 1/2 and y was 1. Yes, was another maximum. Well, let's look at one more example. Let's look at let's say find min max of let's do a very simple example. Let's do x squared plus y squared is our function. So this was, let's call it f again. On, well, let's let's look at it on the unit circle. So let's on x squared plus y squared equals 1, right? Well, so here say, well, let's find the critical points inside. F sub x as 2x, f sub y as 2y. So 2x equals 0, 2y equals 0. That means that x equals 0 and y equals 0. All right. So that means 0, 0 is the only critical point inside, and let's and the function is 0 at the origin, right? Well, let's look at the boundary. So what is the boundary? What is this? This is the unit circle. This is sorry. I wanted to write this thing. Sorry, on inside the unit circle. Sorry, not just equal. That's the boundary. I wrote down what the boundary was, right? But I wanted this set over here. So the unit circle, the boundary over here is when I sort of had the boundary in my mind already. The boundary is where it's equal over here, the inside, that's where x squared plus y squared is less than 1, right? Now, this inequality does define a closed and bounded set. It's bounded by 1, right? It's everything is within distance of 1 of the origin, and it's closed because it does include the boundary, because of this is less than or equal to. Okay, so we found inside we have a critical point, and that's where it's 0. So let's check off what what is the function on this boundary. Well, if f is x squared plus y squared, then on x squared plus y squared equals 1, f is, well, it's x squared plus y squared, and that's equal to 1, so it's f is just equal to 1 everywhere on here, right? So, all right, so that means that it achieves a minimum at the origin, right? I didn't really have to check with the second derivative test, just like in one variable. If I find all the places where minimum and maximum could occur on a closed and bounded region, then I'm good. Then I just need to pick the biggest one and the smallest one, and that tells me what's the minimum and the maximum, right? So I didn't really need to check. If you can, it's actually a local minimum by second derivative test as well. F achieves minimum at 0, 0, and f at 0, 0 is just 0, right? And f achieves a maximum at any point where x squared plus y squared is equal to 1. And maybe that's a little it sounds a little stupid, because that's, well, that's just what f is, just because I picked f to be really simple. All right. Well, let's that's that's it. Let's look at the graph and see how that looks. So here we have the graph of x squared plus y squared graphed over the inside of the unit circle, and you can see that it has a minimum at the origin. That's the bottom over here, and that's where it's 0, right? See, 0 over here, and everywhere along the unit circle it's 1, right? So we get that's the maximum. That's the most it is. All right. So so that's basically the way that we figure out minima and maxima of functions in several variables. Basically, what you do is you generally have some sort of a region. If it's a closed and bounded region, what you do is you look at what the boundary is. You first look for critical points inside, and then you parameterize bits of the boundary and try to figure out if you have minima and maxima on the boundary, where you really start it sort of has one less dimension. So if we're starting with 2 variables, then the boundary is going to be a set of curves, and so then it's basically just calculus. It's one-dimensional calculus, right? Calculus 1. And in general, it's basically you're going to start with 3 variables. Then the boundary is going to be 2-dimensional, And so you have to repeat this process a bunch of times, right? If you were, so for example, if you had a cube and you wanted to optimize some function over a cube, well, you'd first figure out the critical points inside, then you'd have to parameterize the faces, right? And there are 6 faces of a cube. Well, for each face, you'd also have to figure out the minima and maxima on the sides of each face, right? And you know how many how many edges there are in a cube. Well, there are 4 on top, 4 on the bottom, and 4 vertical ones, right? So that's 12. So it gets complicated. You basically have to do 12 one variable maximizations, then 6 two variable optimizations, and 1 3 variable optimization. Yeah, it's a little annoying. Now there is another technique that can be used to minimize and maximize over the boundary. If I have something defined by some equation, like a curve of the boundary, called the Lagrange Multipliers, that will skip, but that's sometimes easier than trying to parameterize. Actually, oftentimes it's easier than trying to parameterize. So it's not as bad, but it does get more and more complicated as you get into more real world examples. All right.